So now let's take a look at this table. It's a little hard to read, it's a little bit small. You probably want to take a look at your PowerPoint files so you can see these subscripts better. But it's not hard to construct. So the table that you were given in rows, we will flip on its side and write the same table in columns. Column 1 will be the x values I have. Column 2 will be the functional evaluation of those same x values. Might have been easier if I just called it y0, y1 down to y3. The next term is the first ordered divided difference, with each of the pairs indicated in this particular order. We are going to name these first order divided differences so we can use them again. We'll call them delta. This delta involves x0 and x1, so that's why I've called it as such. And this delta is involving x1 and x2, and that's why I've subscripted it in that manner. And again, this one is involving x2 and x3. The nice thing about the method is once you get a value, you can reuse it. To get my second order divided difference, I just do a divided difference of the values in the preceding column. I'll take this value minus this value divided by the span over which the x's are used. This delta uses all the x's from x0 to x2, and so I'm dividing by x2 minus x0. Same thing with the second divided difference. It's using the last three values, and so I'm calling it delta squared, or my second order divided difference, using x1, x2, and x3. And the same formula is used here, except with the three rows that are indicated. The last divided difference I'm interested in is one that uses everything, but it's going to be a divided difference of second order divided differences. So here we have a second order divided difference involving x1 through x3 minus a second order divided difference using x0 through x2, all divided by x3 minus x0 because that's the total span over which it applies. That looks messy, that looks complicated, but computationally it's not bad. So what do I do with these values? Well, I'm going to use only the first elements in each column. Let's take a look at how we lay that out. This will be my third order polynomial with a constant term, a linear term, quadratic term, and a cubic term, all in terms of these differences. The coefficients will be the divided difference, either third order, second order, or first order. If you had more points to work with, you just make the table bigger, but do exactly the same thing. Now, I think an example is needed here to get all these deltas and f's and x's out and subscripts, because the procedure is really quite straightforward. It's just the jargon is a little bit abstract. So let's take a look at a specific example in the following slide. Here is a table of 4 entries of the x and the y values. I follow the procedure by taking the x values and stick them in the first column. I take the function of each of those values and stick it in the second column. Not hard. Create the first divided difference. That's going to be just 13/4 minus 3 divided by 3/2 minus 1. Calculate it out, I get 1/2. Now I need my other two first order divided differences, and I do the same thing. The second one uses these two rows, and the third one uses these two rows here. And if you do the calculations in the same way, you get 1/6 and minus 2/3. Now I need to get my second order divided differences. Just as easy as the first order. Okay, I'll take this second row minus the first row and divide it by the two x values that straddle all the data I'm using, which would be x2 and x0. And that goes in the denominator, and we get a 1/3. Do it again with the last 3 rows. How do I do it? Well, I just start with my first order divided differences, taking minus 2/3 minus 1/6, and divide it by 2 minus 3/2, and I get minus 5/3. And finally, I do the last one by taking the last divided difference I can, minus 5/3 minus 1/3, divided by the whole span, 2 minus 1, which is going to be equal to minus 2. These become my coefficients. The 3 is the intercept. 1/2 will be for the linear term. 1/3 for the quadratic polynomial. -2 for the cubic polynomial. And you see them here. P3 is using a 3 and a 1/2, a 1/3, and a -2. Okay, you notice how these deviations never involved x3. They involved x0, which is 1, x1, which was 3/2 here, and x2, which is a 0. See, we just have an x multiplied here, which is x minus 0. But we never use x minus 2. That's just how the algorithm works. So you don't get alarmed if that happens. We now have a polynomial that can be used in cubic interpolation, and it will agree with our Lagrange polynomial exactly. Your homework will help illustrate that. So what if I asked you on some problem to do this as an inverse function? Can you actually create the inverse of one of these polynomials? Now I think I'd panic if this was the first time I took this class and somebody thought I was going to do that, but it turns out to be really easy. All I've got to do is basically flip the table over. I'm going to call x g of y, and I'm going to call f of x y. So here's the same table. I'm just reversing the roles of the independent and dependent variables. Then flip them over so they're in the order that I'm used to. I now have y and g of y. G is the inverse of f by nature because it's running the table backwards. Now, if you think about that, there is absolutely nothing different to do than we already did. Just run the Newton procedure normally with this upside down table and you'll get the inverse. Now that's pretty nice. So you can interpolate both going forward and backwards using the Newton method, and it's the same amount of work either way. Well, to show you it's not too bad, let's do a homework problem. We're going to go to the ordinary exercises in 4.1 and do problem 1. Now you need to do it twice. You're going to have to first do that as a Lagrange polynomial using the methods that we did in 4.1a, and then using the methods we just looked at in 4.1b, use the Newton approach, and you better come up with the same result. Now I'm actually not asking you to prove they're the same, I'm just asking you to come up with both forms, but if you try any points in those two forms, you'll see that they do exactly the same thing. If you'd like some extra credit, go over to problem 8 and try that one just to give you a little more exercise, but on this one just use Newton's method and you can get an extra 10 points for that. Well, I think we've had enough, probably beat you up enough on this section. We are now completely done with interpolation, and we will move on to our next section, which will be differentiation next time.